Hello student, myself Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District, Jalna. Today we will see X-rays, semester 3rd, course code number 202, paper number 8, Modern and Nuclear Physics. Now see the absorption of X-rays. Laue's experiment. The absorption of X-rays. When a monochromatic narrow beam of X-ray passes through a matter, part of it is absorbed and the remaining part is transmitted. Now figure shows the study of absorption of X-rays. Now the X-rays produced by an X-ray tubes are made into a well-defined narrow beam by passing them through the two slits S1 and S2 as shown in figure. Now see, that is a X-ray tube that produces the narrow X-ray beam are through this S1 and S2. These are the lead sheets. Now the beam is then monochromatized by Bragg reflection from a chamber which measure the ionization current. Now see, that is the ionization chamber which measure the ionization current. The strength of the ionization from a chamber which measure the ionization current. The strength of the ionization current is measure of the intensity of X-rays. Also a sheet of the absorption material is placed in the path of the X-ray. See here, that is a absorber which are placed in between this S1, S2 and ionization chamber. Now before it enters the ionization chamber, the ionization current and ionization intensity of X-rays is reduced by passing through the absorption sheet, and the absorption coefficient can be calculated by using the 2 ionization current is I upon I0. Now see, let I0 be the initial intensity of a homogeneous X-ray beam incident normally on an absorber sheet, and I be the intensity after the beam has traveled a thickness x as shown in figure. See, that is I0 is the initial intensity of homogeneous X-ray beam, and I be the intensity after the beam travel a thickness x, see here, of the absorber sheet. If di is the further decrease in intensity over a thickness dx, see here, that is the intensity di over a thickness dx as shown in figure, then minus di upon dx gives the rate of decrease of intensity with thickness is proportional to intensity I. Therefore minus di upon dx is directly proportional to intensity, that is the I, and di by dx equal to minus mu into x, where mu is the proportionality constant and it is called the absorption coefficient of the absorber. Now di upon I equal to minus mu into dx. So integrating equation, we get integral of di upon I equal to integral of minus d mu into dx equal to minus mu integral of dx, taking this mu is outside from integration. So here now log of I to the base e is equal to integral of this minus mu into integral of dx is minus mu x plus c. Now where c is a constant of integration. To obtain value of c, consider x equal to 0 and I equal to I0. Then equation 4 becomes log of I0 to the base e is equal to c. Now putting the equation 4 becomes log of I to the base e is equal to minus mu x plus log of I0 to the base e, or log of I to the base e minus log of I0 to the base e is equal to minus mu x. Now it is equal to log of I upon I0 is equal to minus mu x, or I upon I0 equal to e raised to minus mu x, or I equal to I0 e raised to minus mu x. It is seen that intensity of X-ray beam decreases exponentially with the thickness of the absorbing material, that is shown in graph. Now absorption coefficient is equal to the fractional decrease in the intensity of X-rays per unit thickness of absorber sheet. So mu equal to minus di upon I upon dx. Now Laue's experiment. Von Laue in 1930 suggests that a crystal should act as a three-dimensional diffraction grating for an X-ray beam. He, with Frederick and Kinping, passed a small beam of X-rays through zinc blende ZNS crystal and allowed the emerging beam to fall on a photographic plate as shown in figure. Now this is a basic diagram for Laue's experiment. See here, we have a X-ray tube that produces X-rays from this X-ray tube. These X-rays are turned into a very fine beam by using lead sheets in which you have a small pinholes. Due to these small pinholes, all the X-rays are absorbed except for these X-rays which are going through these pinholes. So the X-ray is basically turned into a small fine beam of parallel X-rays. So this set of parallel X-rays, they are bombarded on a crystal, that is ZNS crystal as shown in figure, which is to be analyzed, and this is the crystal which are analyzed to understand what is crystal structure. When the X-rays they fall on the crystal, they get diffracted and you get a pattern on the screen, and this is screen that shows the pattern, that is a photographic plate, is unique for every crystal, and you have a large number of bright spots as you can see, and this arrangement of bright spot is unique to a particular crystal, and this arrangement of bright spot is known as Laue's spot, and on the basis of Laue's spot you can find out the crystal structure. This is caused by the diffraction of X-rays through the crystal and is similar to that expected by Laue from a three-dimensional grating. The narrow beam of X-ray emerging from slit was allowed to fall on a crystal plate, that is zinc sulfide, that is ZNS, behind which was set of a photographic plate was exposed to X-rays for a long time, and then it is developed, and the developed plate shows diffraction pattern consisting center spot surrounded by regularly arranged series of spots. A black spot at the center is due to directly coming X-rays, and this pattern is proof of wave nature of X-ray, and this pattern is useful to determine the microscopic nature of solid matter. It is helpful to locate different planes in crystal lattice which contain large number of atoms. Such diffraction pattern consists of a central dark spot surrounded by a series of smaller spots arranged in symmetrical order, and this symmetrical pattern of spot is known as Laue's pattern. Thank you.